Welcome to today's paper reading. Today's paper is titled, On the Topology Awareness and Generalization Performance of Graph Neural Networks. This paper was published at ECCV 2024 by Junwei Su and Chuan Wu from the Department of Computer Science at the University of Hong Kong. The abstract highlights the importance of graph neural networks, GNNs, as a leading tool for learning representations of graph-structured data. A key feature of GNNs is their topology awareness, which allows them to leverage the inherent topological properties of graphs. Despite their empirical success, the impact of topology awareness on generalization performance remains underexplored, especially in node-level tasks that do not assume independent and identically distributed ID data. The paper introduces a comprehensive framework to characterize the topology awareness of GNNs across various topological features. This framework reveals that enhancing topology awareness may not always be beneficial, as it can lead to unfair generalization across structural groups. The paper also presents a case study using the shortest path distance metric on benchmark datasets, confirming these theoretical insights and demonstrating the practical application of the framework in solving the cold start problem in graph active learning. Graph neural networks, GNNs, have become a leading class of models for graph-structured data, demonstrating significant success across various domains such as chemistry, biology, and social networking. A defining feature of GNNs is their use of a spatial approach through message passing, which allows them to preserve structural information from the underlying graph, known as topology awareness. This characteristic is crucial for tasks like node classification. However, there is a lack of theoretical understanding, particularly in semi-supervised settings where data dependencies differ significantly. The concept of structural subgroup generalization aims to quantify how GNNs generalize across different structural subgroups within the data, which is essential for their application and development. Despite its importance, the relationship between topology awareness and structural subgroup generalization remains poorly understood. Figure 1 provides a visual representation of the learning process within a two-layer graph neural network, GNN. The core mechanism illustrated is the message passing process, which utilizes the graph structure to aggregate information from neighboring nodes. This aggregation process results in the generation of a representation or embedding, denoted as HA, for the target vertex A, which is highlighted in red. This figure effectively demonstrates how GNNs leverage the topological features of a graph to create meaningful node representations, which are crucial for tasks such as node classification and graph-based learning tasks. The topology awareness of GNNs is largely inspired by the Weisfeiler-Lehmann isomorphism test, which uses graph structure for information propagation. This has led to a focus on the expressive power of GNNs, aiming to preserve more structural properties in learned representations. However, the exact impact of increased topology awareness on GNN's generalization performance is not well understood. Relatively few studies have explored this in node-level tasks, using frameworks like statistical learning to provide generalization bounds. Our proposed framework aims to fill this gap by using the concept of distortion in approximate metric embedding to link topology awareness with generalization performance. The proposed framework investigates the relationship between topology awareness and generalization performance in graph neural networks, GNNs. The framework uses metric distortion to characterize the topology awareness of GNNs. This characterization helps in understanding the relation between the topology awareness of GNNs and their generalization performance. The GNN preliminaries include the definition of a graph G with nodes V, edges E, and node attributes X. Each node V has an m-dimensional attribute vector 15 and a label Y V. The structural subgroup concept involves a metric space, VDS, that captures the similarity between nodes based on structure S. The structural distance ds measures the distance between nodes or groups of nodes, and the partition scheme VK defines subgroups based on their distance to the training set. The main results of this study highlight the relationship between the generalization performance of GNNs and the structural distance between subgroups and the training set. Theorem 1 demonstrates that the generalization risk depends on the empirical training loss, the structural distance, and the distortion of GNNs. This reveals a new perspective on the link between topology awareness and generalization performance in GNNs. Theorem 2 further shows that GNNs exhibit unfair generalization performance when comparing subgroups with significant structural distance differences to the training set. This leads to accuracy disparities among different subgroups, with performance being better for those structurally closer to the training set. Additionally, the study connects these findings to deep learning spline theory, suggesting a valley effect in the embedding space where representations closer to the training set perform better. This connection validates the derived results and provides further insights into the generalization and fairness of GNNs. Figure 2 illustrates the loss landscape in the embedding space induced by different training sets. The figure demonstrates that the selection of the training set significantly affects the test losses. Specifically, when vertices A and D are chosen as the training set instead of B and C, the test losses are observed to be smaller. This reduction in test losses is attributed to the smaller average distance between the selected training set and the other vertices. The neighborhoods of the embeddings HA and HD are shown to cover a larger portion of the embedding space, which contributes to the improved test performance. In this case study, the primary objective is to validate the predictions and effectiveness of the proposed framework using the shortest path distance. The study aims to demonstrate how the framework can be applied to real-world scenarios and understand the generalization performance of GNNs across different structural subgroups. The methodology involves utilizing the shortest path distance to examine structural subgroups and evaluate GNN models. The findings indicate that GNNs are distance-aware, leading to improved generalization performance and providing an effective solution to the cold start problem in graph-active learning. Figure 3 illustrates the relationship between graph distance, measured by shortest path distance, and embedding distance, measured by Euclidean distance, for 4 representative graph neural networks, GNNs, on 2 datasets, Cora and coauthor CS. The graphs A-D show this relationship for the Cora dataset, while E-H show it for the coauthor CS dataset. The highlighted regions in each graph represent the 95% confidence interval for the regression analysis. The results consistently demonstrate a linear relationship between graph distance and embedding distance across all GNNs and datasets, indicating that the embedding distances are a good proxy for graph distances, which is crucial for understanding the generalization performance of GNNs. Figure 4 illustrates the relationship between graph distance and the accuracy of graph neural networks, GNNs, on 2 datasets, Cora and coauthor CS. In both A and B, it is observed that the accuracy of GNNs tends to be higher for vertices that are closer to the training set, as indicated by the graph distance. This finding supports the notion that GNNs that are aware of distance, i.e., distance-aware GNNs, exhibit better generalization performance. The results validate that graph distance serves as a reliable indicator of how well GNNs can generalize to unseen data, particularly when the training set is structurally similar to the test set. Table 1 presents the accuracy results of 30 independent trials with different train/test pairs grouped by the graph distance DSPD, D\V0, V0. Group 1 includes the 10 trials with the largest graph distance, while Group 3 includes the 10 trials with the smallest graph distance. The table records the average accuracy and variance for each group. The findings indicate that train/test pairs with closer structural similarity exhibit better generalization performance, aligning with the theoretical predictions. Table 2 presents a comprehensive comparison of various graph neural network, GNN, sampling strategies based on graph structure. The results, averaged over 5 trials, show the test accuracy, ACC, and maximum discrepancy, MD, for each strategy on different datasets. The table highlights that coverage-based sampling consistently achieves higher accuracy and lower discrepancy, indicating its effectiveness in initial data labeling. Notably, the bold entries signify the best-performing sampling strategy for each dataset and GNN model, providing valuable insights for selecting optimal strategies in graph-based machine learning tasks. In this work, the authors study graph neural networks, GNNs, and their generalization performance in computer vision and machine learning tasks. They introduce a novel framework connecting GNN structural awareness with approximate metric embedding, providing a new perspective on their generalization capabilities and semi-supervised node classification tasks. This framework helps in understanding GNN generalizability across different graph structures. The author's theoretical findings on structural results are demonstrated through practical performance in a case study on graph distance. Additionally, their findings address the cold start problem in graph active learning and could impact various GNN applications. However, the current approach has limitations, such as interpreting GNN embeddings in terms of metric mapping and focusing on the transductive setting. Expanding the analysis to the inductive setting would provide a more comprehensive view of GNN generalization capabilities. Thank you for watching.